The paper introduces an instruction-based object addition pipeline, named AddSD, which automatically inserts objects into realistic scenes with rational sizes and positions. This pipeline is conditioned on simple text prompts rather than human costly references like bounding boxes. The work contributes in three aspects: proposing a dataset containing numerous instructed image pairs, fine-tuning a diffusion model for rational generation, and generating synthetic data to boost downstream tasks. The first aspect involves creating a removal dataset consisting of original edited image pairs with textual instructions, where an object has been removed from the original image while maintaining strong pixel consistency in the background. These data pairs are then used for fine-tuning the Stable Diffusion (SD) model. Subsequently, the pre-trained AddSD model allows for the insertion of expected objects into an image with good rationale. Additionally, the paper generates synthetic instances for downstream task datasets at scale, particularly for tail classes, to alleviate the long-tailed problem. Downstream tasks benefit from the enriched dataset with enhanced diversity and rationale. Experiments on LVIS val demonstrate that AddSD yields an improvement of 4.3 map on rare classes over the baseline. The proposed AddSD pipeline begins with the creation of a removal dataset containing image pairs via random instance removal. These datasets are then employed to fine-tune image-to-image generation using the Stable Diffusion model. Next, generation occurs on the entire dataset by sampling rare classes to alleviate the long-tail issue. Finally, synthetic images are integrated into the original dataset to enhance downstream tasks. The paper also discusses the limitations, assumptions, and future work discussed in the research. It highlights novel ideas, significant findings, and important arguments presented in both pages. The equations, algorithms, and mathematical concepts are explained with precision, detailing their purpose and significance. The summary efficiently covers information from figures, tables, and graphs, connecting the content of these two pages and showing the flow of ideas. The proposed method, AddSD, is a flexible and general approach for inserting objects into real images at rational positions using text instructions. This instruction-based addition pipeline simplifies the process by eliminating the need for costly human layout design. The authors introduce an instructed image pair creation strategy, forming a removal data set by removing objects from an image, which maintains high visual plausibility and positional rationality. The authors discuss related work in diffusion models for image generation, highlighting their limitations in generating new objects in images and their reliance on attention guidance. They also discuss instruction tuning, a fine-tuning technique that adapts pre-trained models using human instructions, and its applications in vision language models and image editing. The authors propose a novel approach to synthetic data augmentation, leveraging the inverse operation of removing objects from the scene to generate superior data pairs with high consistency and rational distributions. They argue that existing methods struggle with retaining the pasted object and ignoring the rationality of added objects, resulting in reduced detection accuracy. The AddSD pipeline consists of three stages: creating image pairs by removing objects, fine-tuning AddSD, and generating synthetic data for downstream tasks. The authors use Llama, an inpainting model, to remove existing objects from real images, creating image pairs with consistent content but differing in local regions. They leverage ChatGPT to generate various instruction templates, enhancing user experience and usability. The authors evaluate their method using CenterNet2 on Coco val and LVIS val, showing consistent improvements, especially a 4.3 map increase on rare classes on the LVIS benchmark. They argue that their method is a general and flexible approach, where each component can be replaced by state-of-the-art models. The authors highlight the limitations of existing methods, including the inability to independently add targets without reference objects, reliance on manually designed restrictions, and the lack of realistic image pairs that maintain positional and contextual consistency. They propose AddSD as a solution to these challenges, enabling the automatic addition of expected objects based solely on text prompts in a human instruction format. The proposed AddSD model is a diffusion-based approach for rational object addition in images. The model is fine-tuned on a constructed removal dataset, which consists of original edited image pairs created through an object removal process. The removal process involves removing single or multiple instances from images, and the resulting image pairs are used to train the diffusion model to learn rational object addition. The fine-tuning process utilizes a stable diffusion model, specifically instruct pix2pix, which is conditioned on both image and text instructions. The model takes an input image and generates a new image with the added object, based on the provided text instruction. The optimization objective is to minimize the difference between the predicted noise and the actual noise. The model is trained on a dataset of real images, such as COCO and LVIS, and is evaluated on downstream tasks such as object detection and instance segmentation. The results show that the AdSD model can effectively generate synthetic data that improves performance on these tasks, particularly in addressing the long-tail problem. To ensure rationality in the generated images, a superlabel-based sampling strategy is proposed. This approach restricts the category of the added object to a specific superlabel, and then randomly samples a sublabel within that superlabel. This ensures that the added object is contextually relevant to the original image. The AdSD model is compared to existing works on synthetic data augmentation, such as copy-paste and XPaste. The results show that AdSD is a simple and effective approach that can generate high-quality synthetic data without requiring complex pipelines or predefined layouts. The model's ability to generate rational and contextually relevant synthetic data makes it a valuable tool for improving performance on downstream tasks. The proposed approach can be used to augment existing datasets and improve the robustness of computer vision models. Equation 1 represents the noise latent ZT, which is obtained by adding noise E to the latent embedding Z. Equation 2 represents the optimization objective, which minimizes the difference between the predicted noise and the actual noise. Figure 3 visualizes the removal process, showing the original image and the edited image with the removed object. Figure 4 illustrates the superlabel-based sampling strategy, showing the process of collecting supercategories and sampling labels. Figure 5 compares the AdSD model to existing works, highlighting its simplicity and effectiveness. AdSD is a novel method for generating synthetic images with new instances, leveraging a diffusion model to create diverse and realistic images. This approach addresses the issue of lacking annotations for newly added objects by using a grounding method to locate these instances. The generated images cannot be used directly for training detectors due to the absence of annotations for the added objects. To address this, the authors employ a grounding method to locate the added instances, using their labels as queries. For the original instances, which are expected to be preserved in the synthetic images, they directly copy all ground truth boxes from the real images into the generated ones. The authors also tested several data filtering strategies from previous works, such as using aesthetic scores or clip scores to filter out poor quality images, using classification scores to remove poor quality instances originally present in the real images, and deleting objects that are either too small or too large. However, these methods did not yield further improvements. Therefore, they decided not to use any additional filtering strategies for simplicity. To train the generated data, the authors follow Gen 2 DET and use a batch sampling strategy instead of directly mixing the generated data with the original data using a weighted sampler. This approach avoids additional processing on the mask loss when the current batch is sampled from synthetic data. The synthetic data pipeline of AdSD and other methods is depicted in Fig. 5. Copy-paste and XPaste both require a segmenter to filter out masks of the target to be pasted. Their difference lies only in whether the target is cropped from a real image or generated by Stable Diffusion. Then, they are pasted onto another real image with strategies such as random pasting or choosing the content with more empty space. Their pipeline is complex and thus time-consuming during the training of detectors. On the contrary, AdSD, once trained on an AdSD with RemovalDataset, requires only one step to generate instances onto it with randomly sampled labels as instructions. The authors evaluate the image editing performance through a user study and several generation metrics, comparing it to other commonly used image editing methods. They also compare the downstream performance of models trained with their generated data against other synthetic augmentation methods. Additionally, they conduct ablation studies on the components of ADSD. Finally, they provide qualitative analysis through visualization comparisons. The proposed ADSD method demonstrates significant improvements in object detection and instance segmentation tasks on the LVIS and COCO datasets. By generating synthetic data through a rational process, ADSD alleviates the long-tail problem and enhances performance on rare classes. The method is evaluated on various backbones, including faster RCNN, mask RCNN, and CenterNet2, and consistently outperforms existing techniques. The results in Table 3 show that ADSD surpasses the baseline by 4 box AP and XPaste by 3.8 box AP on the LVIS dataset, particularly on rare classes. Similarly, Table 4 demonstrates that ADSD achieves the highest scores for both box AP and mask AP on the COCO dataset. The growth rate of rare classes generated through ADSD is also higher, as shown in Fig. 7. The ablation study in Section 4.5 explores the effects of synthetic data sampling ratio, batch sampling, and training schedule on performance. The results indicate that a sampling ratio of 20% yields the best performance for mixed learning on COCO, and that batch sampling demonstrates better results than normal mixture. The training schedule is also extended from 4 times to 8 times, and the results show that ADSD achieves continuous improvement with the extended training time. The superlabel selection strategy is also proposed to generate samples for rare classes. By selecting labels in the range of superlabels of the original instances in the images, the generated instances and original instances exhibit relatively similar characteristics, reducing the occurrence of unreasonably generated instances. The results in Table 9 demonstrate an effective enhancement in performance using superlabels. The mathematical concepts and equations underlying the ADSD method are not explicitly presented in these 2 pages. However, the results and discussions suggest that the method relies on a combination of generative models and object detection architectures to produce synthetic data that can be used to augment real-world datasets. The use of superlabels and batch sampling strategies also implies a reliance on techniques from machine learning and computer vision. Overall, the ADSD method presents a promising approach for enhancing performance in object detection and instance segmentation tasks, particularly on rare classes. The results and discussions in these 2 pages provide a comprehensive understanding of the method's effectiveness and limitations, and highlight the potential benefits of using synthetic data augmentation techniques in computer vision applications. ADSD. Rational generation without manual reference. The proposed method, ADSD, demonstrates significant advancements in instruction-based object addition, seamlessly integrating objects into realistic scenes using only textual instructions. The method's effectiveness is evaluated on various datasets, including COCO and LVIS, and compared to other image editing methods, such as Instruct Pix 2 Pix and Magic Brush. Table 9 presents the results on COCO under CenterNet2, comparing the label selection strategy during data generation of ADSD. The results show that ADSD achieves competitive performance with and without superlabels. Table 10 illustrates the scalability of synthetic data augmentation with samples generated by ADSD in downstream tasks, highlighting the benefits derived from diverse training samples. Fig. 8 compares the visualization of editing results between ADSD and other image editing methods. ADSD maintains background consistency while providing diverse generalization, whereas other methods produce similar samples. For example, in the first image, ADSD generates dogs with different poses and creates fire hydrants with various locations and colors. Fig. 9 visualizes ADSD-generated results under rich instructions, demonstrating the method's ability to learn from instruction and generate more diverse images with reasonable placement of new objects. The results show that ADSD can handle attributes as inputs for generating more detailed instances, distinguish positional relationships between objects, and generate different numbers of targets by prompting with direct numbers or quantity descriptors. However, there are some limitations to ADSD. The training datasets can be affected by cases where the object is not removed naturally, such as residual blur or shadows, see Fig. 10. Additionally, processing large targets is more challenging, as removing a large instance can result in unsatisfactory inpainting, which reduces dataset quality. The proposed method has the potential to advance the field of visual generation and has various applications in computer vision and artificial intelligence. Future work can focus on addressing the limitations of ADD-SD and exploring new applications of the method.